In this part 8 of transportation problem series, we will discuss iterations to optimal solution, which is phase 2 of transportation simplex method. The initial feasible solutions we set in the preceding 6 videos are considered as phase 1 of transportation simplex method. So what's the focus of phase 2? Phase 2 of transportation simplex method is a procedure for iterating the initial feasible solution identified in any of the methods in phase 1. That's northwest corner cell method, least cost cell method, or Begel's approximation method to the optimal solution. The iteration procedure requires that the number of occupied cells of the initial feasible solution under inquiry must be equal to m plus n minus 1, where m is the number of rows in a given initial feasible solution or the number of sources, and n is the number of destinations or the number of columns in a given initial feasible solution. If the initial feasible solution is degenerate with less than m plus n minus 1 occupied cells, add artificially occupied cell or cells so that m plus n minus 1 occupied cells exist in locations that enable use of MODI method. MODI method is modified distribution method, which is used to identify the incoming cells. For the iteration procedure to continue, the total number of occupied cells in a given initial feasible solution should be 1 less than the sum of the total columns and total rows. If not, we have to add 1 or more artificially occupied cells with 0 assignments. For better exposition of this iteration procedure, let's dive into the steps of iteration. Step 1. Identify the incoming cell, which is a currently unoccupied cell or unoccupied route, where the flow allocation will cause the largest per unit reduction in total cost. The modified distribution method is used for identifying this incoming cell. The modified distribution method requires to define an index U sub I for each row of the W and an index V sub j for each column of the W, and then calculates the cost coefficient of each occupied cells and their unit costs as U sub I plus V sub j is equal to C sub ij. For the initial feasible solution of electricity distribution to 3 cities from 3 plants and 1 external network, which we already set in part 7 of this installment, the equation of the cost coefficient and their unit cost for each occupied cell can be expressed as follows. First, let's assign row indexes, that is U sub 1, U sub 2, U sub 3, and U sub 4 for the 4 rows in the W, and the column indexes V sub 1, V sub 2, and V sub 3 for the 3 columns. The only occupied cell in row 1 is the one at the intersection of row 1 and column 3. So the equation of the row index for the first row, that's U sub 1, column index for the third column, that's V sub 3, and the unit cost of this cell, that's 400, can be expressed as U sub 1 plus V sub 3 is equal to 400. Similarly, the equation of the cost coefficients and the unit costs for the 2 occupied cells in row 2 can be expressed as U sub 2 plus V sub 1 is equal to 300 for the cell at the intersection of row 2 and column 1, and U sub 2 plus V sub 2 is equal to 320 for the cell at the intersection of row 2 and column 2. By the same analogy, U sub 3 plus V sub 2 is equal to 480, and U sub 3 plus V sub 3 is equal to 450 for the occupied cells in column 2 and column 3 of row 3 respectively. For the occupied cell under column 2 of row 4, the equation is U sub 4 plus V sub 2 is equal to 1000. In such calculations, since the index variables are one more than the equation, it's always chosen the first row index variable, that's U sub 1 equal to 0. Once U sub 1 is set as 0, we can calculate the other index variables since the number of variables will be equal to the number of equations. In this initial feasible solution, we have 7 unknowns, that's 4 row index and 3 column index, but the equations we set are 6. Since the number of unknowns are greater than the number of equations, it's impossible to determine the unique value for each unknown. To overcome this problem, we have to set one of the unknowns, that's conventionally the index of row 1 equal to 0. The equations we set so far are used to determine the row and column indexes. In order to determine the incoming cell, we have to calculate the net evaluation index, that is E sub ij, for each unoccupied cell by using the formula E sub ij is equal to C sub ij minus U sub I minus V sub j, where E sub ij is the net evaluation index, C sub ij is the unit cost for a given unoccupied cell, U sub I is the row index, and V sub j is the column index. Equations of the net evaluation index for the unoccupied cells of a transportation problem on electricity distribution to 3 cities from 3 plants and 1 external network can be expressed as follows. We have 2 unoccupied cells in row 1, so the equation of their net evaluation index can be expressed as E11 is equal to 600 minus U sub 1 minus V sub 1 for the cell at the intersection of row 1 and column 1, and E sub 1 2 is equal to 700 minus U sub 1 minus V sub 2 for the cell at the intersection of row 2 and column 2. In similar manner, the equation of the net evaluation index for other unoccupied cells can be expressed as E23 is equal to 350 minus U2 minus V3. E31 is equal to 500 minus U sub 3 minus V sub 1. E43 is equal to 1000 minus U sub 4 minus V sub 3. If all the values of the net evaluation index are greater than or equal to 0, the solution is optimal. If not, choose the incoming cell and then continue to step 2. The cell with the smallest values of the net evaluation index is considered as the incoming cell. The steps we went through so far can be considered as the sub-steps of step 1. Once we identify the incoming cell in these steps, we have to proceed to step 2 to identify the outgoing cell. That's step 2. Identify the outgoing cell and determine the adjustments necessary for the other occupied cells by using stepping stone method. This step by itself has the following sub-steps. Sub-step 1. Draw a closed path or loop starting from an occupied cell. The right angle turn in this path is allowed only at occupied cell and at the original unoccupied cell. Mark plus and minus signs alternatively at each corner starting from the original unoccupied cell. Sub-step 2. Select minimum allocated value among all negative positions on a stepping stone path as an outgoing cell and assign its value to the incoming cell. Sub-step 3. Add this value to the other occupied cells marked with positive sign and subtract it from other occupied cells marked with negative sign. For better understanding of these steps and their sub-steps, let's proceed to calculate optimal solution for the problem. As you can refer back to part 5 and part 7 of this installment, the initial feasible solution we set by using least cost cell method and Google's approximation method looks like this, and the resulted total cost is 52,180 birr. So let's go through the steps of iteration to find the optimal solution for this initial feasible solution. Step 1. Calculate the row index, that is U sub I, column index, that's V sub j, and the net evaluation index, that's E sub ij, in order to determine the incoming cell. Let's assign the row indexes as U sub 1, U sub 2, U sub 3, and U sub 4, and column indexes as V sub 1, V sub 2, and V sub 3. First, let's determine each row and column index by using the formula. Row index, that's U sub I, plus column index, that's V sub j, is equal to unit cost for the given cells, C sub ij. When we check degeneracy, number of rows, that's 4, plus number of columns, that's 3, minus 1. 4 plus 3 is 7, minus 1 is 6, which is equal to the number of occupied cells. So we can continue without adding any artificial occupied cells. As we discussed above, the row index for row 1 is always equal to 0. The only occupied cell in row 1 is the one located under column 3. Thus, the column index of this column 3 can simply be calculated by using the formula. The assigned row index of row 1, that's 0, plus column index of column 3, that's V3, is equal to unit cost of this cell, that's 400. This implies V3 is equal to 400. Once V3 is determined, we will go down the column to look for another occupied cell. So the occupied cell in this column is the one at the column's intersection with row 3. Hence, we can calculate the row index of the third row, that's U3, by using the formula. U3 plus column index of third column, that's 400, is equal to unit cost of the cell, that's 450. This implies U3 is equal to 450 minus 400, which gives us 50. After determining the third row index, we can calculate the column index of all occupied cells in this row. From the two occupied cells in this row, the one with 480 per unit cost is the one its column index is not determined. Thus, the third row index, that's 50, plus second column index, V2, is equal to 480. V2 is equal to 480 minus 50, which gives us 430. Once we determine V2, we can calculate the second row index, that's U2, and the fourth row index, that's U4. Because these are the two occupied cells in this column, hence U2 plus second column index, that's 430, is equal to 320. This implies U2 is equal to negative 110. And U4 plus second column index, again, that's 430, is equal to 1000. This implies U4 is equal to 570. V1 is the only column index not determined at this stage. If we go down in this column, we can find occupied cell at row 2. Hence, this column index can be calculated as V1 plus row index of second row, that's negative 110, which is equal to unit cost of this cell, that's 300. This implies V1 is equal to 300. Taking negative 110 to the other side of equality, you get plus 110. 300 plus 110 give us 410. The intent for calculating row and column index is to determine the net evaluation index for all unoccupied cells by using the formula net evaluation index for the unoccupied cells, that is E sub ij, is equal to unit cost for that cell, that's C sub ij, minus row index, that is U sub I, minus column index, that's V sub j. We have two unoccupied cells in row 1. The net evaluation index of the unoccupied cell under column 1, that's E11, is equal to the unit cost of this cell, that's 600, minus the row index, that is 0, minus the column index, that's 410. The difference of these numbers gives us 190. The net evaluation index for the unoccupied cell under column 2 of row 1, that's E12, is equal to the unit cost of the cell, that's 700, minus row index, that is 0, minus column index, that's 430, which is equal to 270. Plant 2 to CT3 root is the only unoccupied cell in row 2. Thus, its net evaluation index is E sub 23 is equal to unit cost, that's 350, minus column 3 index, that's 400, minus row 2 index, that's negative 110. Here, negative times negative give us positive 110. 350 minus 400 is negative 50. Negative 50 plus 110 gives us 60. The net valuation index for unoccupied cell in row 3, that's E31, is equal to unit cost of the cell, that's 500, minus row 3 index, that's 50, minus column 1 index, that's 410. The difference of these values gives us 40. The net evaluation index for the unoccupied cell in row 4, that's E43, is equal to unit cost of the cell, that's 1000, minus column 3 index, that's 400, minus row 4 index, that's 570, which is equal to 30. Since all the calculated net evaluation index values are positive, the solution is optimal. These positive values of net evaluation index tell us that if we choose either of them as an incoming cell, we will incur an additional unit transportation cost equal to the values of that calculated net evaluation index. For example, if the cell at the intersection of row 2 and column 3 is chosen as the incoming cell, the unit transportation cost is increased by 60 per. Therefore, the optimal solution or the minimum distribution cost is 52,180 per, which is already determined as the total cost of initial feasible solution obtained by using Vogel's approximation method as well as least cost cell method. From this problem, we learned that the initial feasible solution by itself can be an optimal solution. In part 2 of this installment, the initial feasible solution for this same problem was set by using northwest corner cell method, and the feasible solution looks like this. The total transportation cost of this initial feasible solution is 56,520 per, which is more than the optimal transportation cost by the amount equal to 4,340 per. Thus, it's obvious that this initial feasible solution has to go through some iterations in order to make it optimal. As usual, let's assign the row indexes as U sub 1, U sub 2, U sub 3, and U sub 4, and the column indexes as V sub 1, V sub 2 and V sub 3. The formula for calculating row and column indexes for the occupied cells is U sub I plus V sub j is equal to Cij. As I mentioned above, the row index of row 1 is conventionally set as 0. Once we set row 1 index as 0, we can calculate the column index of all occupied cells in this row. Unfortunately, we have only one occupied cell in this row. That is the one at the intersection of row 1 and column 1. So its column index can be calculated by using the formula row index of row 1, that is 0, plus the unknown or column index of column 1, that is V sub 1, which is equal to unit cost of the cell, that's 600. This implies V1 is equal to 600. The determination of column 1 index will help us to calculate all row indexes of the occupied cell in this column. Again, we have only one occupied cell in this column, that's the one at its intersection with row 2. So second row index, that's U2 plus 600 is equal to 300. This implies U2 is equal to 300 minus 600, which gives us negative 300. As we move to the right of row 2, we can find occupied cell under column 2. Thus, the column index of this second column can be calculated as negative 300 plus V2 is equal to 320. This implies V2 is equal to 320 plus 300, which gives us 620. By using this 620, we can calculate the third row index, that's U3, because the cell at the intersection of row 3 and column 3 is an occupied cell. So U3 plus 620 is equal to 480. This implies U3 is equal to 480 minus 620, or it's negative 140. The other occupied cell in this third row is the one under column 3. Thus, row 3 index, that's negative 140, plus column 3 index, that's V3, is equal to unit cost of this cell, that's 450. This implies V3 is equal to 450 plus 140, that gives us 590. The only undetermined index is the fourth row index, which can be calculated by using third column index and the unit cost at the intersection of row 4 and column 3, that's 1000, meaning U sub 4 plus 590 is equal to 1000. This implies U sub 4 is equal to 1000 minus 590. That gave us 410. In moving forward, we have to calculate the net evaluation index for all unoccupied cells by using the formula net evaluation index, that's E sub ij, is equal to the unit cost, that's C sub ij, minus row index, that's U sub I, minus column index, that's V sub j. The unoccupied cell under column 2 of row 1, which is designated as E sub 1, 2, is equal to unit cost of this cell, that's 700, minus row 1 index, that's 0, minus column 2 index, that's 620. The difference between these values gives us 80. By the same analogy, we can calculate the net evaluation index of the other unoccupied cells as E sub 1, 3 is equal to 400 minus 0 minus 590, which gives us negative 190. E23 is equal to 350 minus negative 300, which is plus 300 minus 590, which gives us 60. E sub 3 is equal to 500 minus negative 140, which is plus 140 minus 600, which gives us 40. And E42 is equal to 1000 minus 410 minus 620, which is equal to negative 30. Since the net evaluation indexes of the two unoccupied cells are less than 0, the solution is not optimal. These negative net evaluation index values tell us that the unit transportation cost will decrease by the mentioned amount if shipments are allocated to these cells. In order to ensure maximum reduction on transportation cost, the cell with least net evaluation index has to be chosen as an incoming cell. The least net evaluation index in this case is negative 190, since the incoming cell is plant 1 to CT3 route. When one unoccupied cell is selected as an incoming cell, one from the occupied cell has to be selected as an outgoing cell. To select this outgoing cell, we have to proceed to step 2. Let's draw a closed loop starting from identified incoming cell and end up with this same cell with a possible right angle turn only at the occupied cell. The incoming cell is the one at the intersection of row 1 and column 3. Starting from this cell, we can draw a straight line either horizontally to the occupied cell under column 1 or vertically down to occupied cell in row 3. Because right angle turn is always possible at the occupied cell. For this case, let's draw a horizontal line to the cell at the intersection of row 1 and column 1. Then we'll down to occupied cell in row 2. And then we will make a right angle turn to the right and extend the line horizontally up to cell under column 2. We can't extend this line out to the cell under column 3 because this cell is unoccupied and hence right angle turn at this cell is impossible. Rather, we have to turn down and draw a straight line up to the immediate occupied cell and then turn to the right and finally back to the starting point. After making this closed loop, the next rule is that starting from the incoming cell, mark plus and minus signs at each corner alternatively, meaning make the positive sign at the incoming cell, negative sign at the cell in the next right angle cell, positive sign at the next turning point, and then negative, then positive, and finally negative sign. At this stage, we have to make sure that all the cells at the turning point are marked either with positive or negative signs. Select the minimum allocated value among all negative positions as outgoing cell. Assign its value to the incoming cell. Subtract it from all negative positions and add to all positive positions. In this case, we have 3 negative positions with allocations of 20, 24, and 12. So the minimum allocation is 12. Thus, the cell with the allocation of 12 is an outgoing cell. We have to remove this 12 from this outgoing cell and allocate it to the incoming cell. Subtracting this 12 from the remaining 2 negative positions will decrease their allocations from 20 to 8 and 24 to 12. Again, adding this 12 to the remaining 2 positive positions will increase their allocations from 16 to 28 and from 18 to 30. At this stage, we conclude this first iteration. We have to continue to the second iteration starting from step 1. That's calculating row and column indexes for the occupied cells and net evaluation index for the unoccupied cell in order to identify the next incoming cell. First, let's calculate the row and column index by using the formula U sub I plus V sub j is equal to C sub ij. Given that row 1 index is 0, 0 plus V1 is equal to 600. This implies V1 is equal to 600. And another occupied cell in this row is the one under column 3. So 0 plus column 3 index, that's V3 is equal to 400. This implies V3 is equal to 400. Second row index, that's U2 plus column 1 index, that's 600 is equal to 300. This implies U2 is equal to 300 minus 600, which gives us negative 300. Negative 300 plus second column index, that's V2 is equal to 320. This implies V2 is equal to 320 plus taking negative 300 to the right side of equal sign becomes positive 300, which gives us 620. U3 plus column 2 index, that's 620 is equal to 480. This implies U3 is equal to 480 minus 620, which gives us negative 140. U4 plus column 4 index, that's 400, is equal to 1000. This implies U4 is equal to 1000 minus 400, which gives us 600. In casting forward, let's calculate the net evaluation index of unoccupied cell by using the formula E sub ij is equal to C sub ij minus U sub I minus V sub j. E12 is equal to 700 minus 0 minus 620, which gives us 80. E23 is equal to 350 minus negative 300, which is positive 300, minus 400, which gives us 250. E31 is equal to 500 minus negative 140, which is positive 140, minus 600, which is equal to 40. E33 is equal to 450 minus negative 140, which is plus 140, minus 400, which is equal to 190. And E42 is equal to 1000 minus 600 minus 620 is equal to negative 220. Still negative 220 is less than 0. Thus, the cell at the intersection of row 4 and column 2 is the next incoming cell. Determine the outgoing cell. Let's draw a closed loop starting from the incoming cell. Move to the occupied cell at the right. then up to another occupied cell in row 1, then to the left up to the occupied cell in the same row, and then down to the immediate occupied cell, then to the adjacent cell at the right, and back to the starting position. Starting from the incoming cell, let's mark plus and minus signs at each corner. We have 3 negative positions with the allocations of 18, 8, and 12. Thus the minimum is 8. So the cell at the intersection of row 1 and column 1 is the outgoing cell. This 8 has to be allocated to the incoming cell. Subtracting 8 from the remaining 2 negative positions decrease their values from 18 to 10 and from 12 to 4. On the other hand, adding these 8 to the positive positions increase their values from 12 to 20 and 28 to 36. In moving to third iteration, let's calculate row and column indexes by using the formula row 1 index, that's U sub I, plus column index, that's V sub j, is equal to unit cost, that's C sub ij, given that row 1 index is equal to 0. 0 plus V3 is equal to 400. This implies V3 is equal to 400. U4 plus 400 is equal to 1000. This implies U4 is equal to 600. 600 plus V2 is equal to 1000. This implies V2 is equal to 400. U3 plus 400 is equal to 480. This implies U3 is equal to 480 minus 400, which gives us 80. U2 plus 400 is equal to 320. This implies U2 is equal to 320 minus 400, which gives us negative 80. And the last one, negative 80 plus V1 is equal to 300. This implies V1 is equal to 300 plus 80, which gives us 380. In calculating the net evaluation index for the unoccupied cells by using the formula Eij is equal to Cij minus Ui minus Vj, E11 is equal to 300 minus 0 minus 380, which is equal to 220. E12 is equal to 700 minus 0 minus 400, which is equal to 300. E23 is equal to 350 plus 80 minus 400, which gives us 30. E31 is equal to 500 minus 80 minus 380, which gives us 40. And E33 is equal to 450 minus 80 minus 400, which gives us negative 30. The only net evaluation index with negative sign is E33. Hence the incoming cell is the one at the intersection of row 3 and column 3. In order to identify the outgoing cell, let's draw a closed loop starting from the incoming cell, down to the adjacent occupied cell, then to the other occupied cell at the left, and then right angle turn to up, finally to the starting point. Starting from the incoming cell, let's mark plus and minus signs alternatively. We have 2 negative positions with the allocations of 10 and 30. The smaller one is 10. So the outgoing cell is the one at the intersection of row 4 and column 3. We have to assign this 10 to the incoming cell. Subtracting 10 from the allocations of other negative positions, that's 30, give us 20. Adding this 10 to 8 as the positive position gives us 18. In continuing to the fourth iteration, let's calculate row and column indexes for the occupied cells, given that row 1 index is equal to 0. 0 plus V3 is equal to 400. This implies V3 is equal to 400. U3 plus 400 is equal to 450. This implies U3 is equal to 50. 50 plus V2 is equal to 480. This implies V2 is equal to 430. U4 plus 1000 is equal to 430. This implies U4 is equal to negative 560. U2 plus 430 is equal to 320. This implies U sub 2 is equal to negative 110. And negative 110 plus V sub 1 is equal to 300. This implies V sub 1 is equal to 410. When we continue to calculate the net evaluation indexes for the unoccupied cells, E sub 11 is equal to 600 minus 0 minus 410, which gives us 190. E12 is equal to 700 minus 430 minus 0, which gives us 270. E23 is equal to 350 plus 110 minus 400, which gives us 60. E31 is equal to 500 minus 410 minus 50, which gives us 40. And E43 is equal to 1000 plus 560 minus 400, which gives us 1160. Since the net evaluation indexes are greater than 0, the solution is optimal. So the resulted optimal cost is equal to 36 times 300 plus 4 times 320 plus 20 times 480 plus 18 times 1000 plus 20 times 400 plus 10 times 450. 36 times 300 is 10,800 plus 4 times 320 is 1,280 plus 20 times 480 is 9,600 plus 18 times 1000 is 18,000 plus 20 times 400 is 8,000 plus 10 times 450 is 4,500. The sum of these values gives us 52,180, which is equal to the optimal solution we determined above. By this, I conclude this episode. Goodbye.